Siri and also get a chance to work with her over this summer. I look forward to once again hearing about her project and also getting a lesson on a little bit of quantum physics, a little bit of chemistry, as well as machine learning. A round of applause for Siri Nalula, please.
Hi everyone, I hope you're doing well. My name is Siri Nalula, and for the duration of this program, I have been working with quantum physics / computational chemistry, and I have been in Dr. Mark Tuckerman's lab at the chemistry department at NYU and Huron Institute of Mathematical Sciences. And so my research project for the past 6 weeks was mainly running simulations of what we call an S2 clathrate hydrate. And to run those computer simulations, we used neural networks and some machine learning. So we'll talk a little bit about those in a little bit later on. Okay. So the agenda for today is to first introduce the clathrate system and to talk about what it is, and then going on to the goal and research question, and then dive into a little bit of the physics background, so some quantum statistical mechanics and path integrals, and then segue into the computer science aspect and machine learning and some neural networks, and then going on to the methods and materials, and so what did I use to run these simulations, and then go on to the results and analysis and future work, and then thank you and acknowledgements. So first of all, what is a clathrate and what is this system, right? So a clathrate is when you have molecules and they're kind of when you put them together, they sort of are trapped within one another such that they create a crystal lattice, and they look like a cage that you see on the screen here. And so in this particular project, the cage was actually a cage of water molecules, and a clathrate always has two components. We always have a guest and a host, and so the host is the cage itself, and it encloses a guest molecule, a guest substance, and so that's just a substance that's lingering around inside and moving around and doing its thing. And so in this research project, the guest was the hydrogen molecules, and they were actually diffusing inside the cage, the two water cages. And so diffusion is just when we have a substance that's going from a higher concentration to a lower concentration and just moving around to find its most happy and stable arrangement. And so what's the goal of running these simulations, and why am I doing that? So it's to run these simulations. In running these simulations, we get a better understanding of hydrogen storage materials. And that's important because it's important if we want to be able to advance hydrogen fuel technology. And that's important because today, the carbon emissions are soaring, and this has zero carbon involved, and it's a very environmentally friendly alternative. And so one of the major problems, however, is that H2 is very hard to store, and it's hard to trap it, and it very easily escapes. And so there's just few good materials that actually do this job well in storing the hydrogen, and so clathrate is one of them. And so why clathrate? Well, one, it traps the H2 nicely, and it allows it to diffuse and distribute evenly so it can move around inside. And then another thing is that it can achieve a 5.5% mass H2, and so that's the target for any viable hydrogen storage material. You want to be able to have at least 5.5% mass inside that. So clathrate achieves all of those three things. And so my research question was, how can we simulate hydrogen diffusion in clathrate using computational methods? And so we'll get into a little bit of physics background first. So first, let's talk about quantum statistical mechanics. So quantum mechanics is just the theory that we use to study small and microscopic things. And when we run these simulations, we get a very nice microscopic description of what's going on inside the clathrate. We can see the individual hydrogen molecules moving around, and we can and the statistics part comes into this when we are able to translate that microscopic description that we see in these simulations to macroscopic observables, and so things like diffusion and free energy, which we'll talk about, I think, like in a couple of slides. And so we're able to make these observations using this microscopic description. And also another characteristic of quantum mechanics is that it's very probabilistic versus classical mechanics, which is deterministic. And so there's a very clear-cut answer all the time with classical mechanics. And so we'll talk about on the next slide with path integrals, right? Like when we have a baseball that's going from like point A to point B, like it's just taking one clear path. There's no argument, there's no debate about that. But when we have something like an electron, that's not always the case. It can be like in many different places at once, and that's so there's a sense of like probability to it. And another very important part about quantum mechanics is wave-particle duality. So that's the idea that when we have like these subatomic particles, they exhibit both wave-like properties and particle-like properties. And so we can actually see that in this picture here when we have like a bunch of electrons going through a screen, and on at the end what we see is like discrete particles, right? But they're also in like a line arrangement, and so that's very typical of a wave. And so that's an example where we can see this wave-particle duality. And so there are also other quantum effects that we only see when we're observing the microscopic world, and two of those are relevant to this particular research project. And one of them is zero-point energy, and the other is tunneling. And so the zero-point energy is the idea that when we're in like a vacuum, there's still, the energy is not at this minimum. The cursor is showing up there, but like it's not at that minimum point. It's actually on the first line or like in between, because we always see some fluctuations happening between different states and we never really know what's going on. So another one is tunneling, and tunneling is when we have like an energy barrier, like a hill. And so in classical mechanics, what we have is the ball really needs to go to the top of the hill. It needs to have that energy to go to the top of the hill and then roll back down. Whereas in quantum mechanics, what we see is a phenomenon called tunneling, where we actually don't need to even cross that energy barrier. We can just go straight through, and I think this visual kind of captures that. And so path integrals is it's like a perspective of quantum mechanics. This is one way to look at it. And so this is when we have like an electron or something like that that's going from point A to point B, and it's not like a baseball going from point A to point B. It's like an electron going from point A to point B, and it has like wave-like properties and particle-like properties. And so once again, there's a sense of probability, and so each path is actually a probability amplitude of a wave function. And wave function, I think on the last slide I forgot, it's a way to mathematically describe that electron or other particle like that. And so we can actually take multiple paths. We can take actually an infinite number of paths. We can take this purple one, this blue one, and this orange path. What we do is we sum over those paths by summing over the probability amplitudes. And a quantum propagator is a function that can give you those probability amplitudes. And obviously there's a weight assigned to each path, because some paths are more likely to be taken than others. And yeah, so you see in this notation here, we have a path from point B to point A, or point A to point B, and then we do something called the trace, and we take the trace of e to the power of like minus beta h, and that gives us a partition function, and so that gives us all the information we need to know or want to know about any particular variable in thermodynamics, and beta is just 1 over kBt. So that's like the constant times the temperature. And going into like going back to the clathrate research project, one way to describe these hydrogen atoms is through ring polymers, and ring polymers just look like this. Do you guys see my cursor here? No? Okay, so that's just like the ring over there, and so that can be like one representation of the hydrogen atom. So we have like 6 beads, that's what they're called, like the little dots around this ring. And we have a finite number of beads because we're doing this on a computer. We can't have an infinite number, so they're connected using through springs. And so that basically represents like a hydrogen atom because we think that they're in that position at any given moment in time because of quantum mechanics and because of that uncertainty. So like the more you know about one variable, the less you know about another, like position or momentum or something. And then so tying that back to path integrals, we actually take the path integral from one bead and then like back to, like going in a circle back to the starting point. So it's actually from A to A and not from A to B. And so when we take like the sum of these paths, we get access to some of these thermodynamic variables that are important to us. And so segueing into the neural networks aspect, so we have like an input layer, and we have some hidden layers and an output layer. That's what a computer is, right? It takes some input and then does something and then gives you an output. And so a neural network does that very well. And we have an input layer, which is just the raw coordinates, and then we apply some symmetry functions to that to give us like the information that we need to know, so radial functions and angular functions. And so those go through the neural network and then generate some energy values that are going to be important to us in the next slide. And so the training data was like, so this was trained before, this was also, so the data was collected before, this was trained before, and so I just used this architecture, this neural network architecture. And so the training data was electronic structure data, and so it was energy and forces at the electronic structure level. And so that's very computationally expensive, so that's why we use a neural network, so we can just take that limited amount of data and then be able to connect the dots and then get the information that we need, so that's one of the benefits. And then it also bypasses the Schrodinger equation, which is another very important equation. So yeah, and so it generates the potential energy, surfaces, and forces at the end, and so we'll see why that's useful here. So we're simulating the diffusion in the cloth rate, right? So according to Chandrasekhar's hopping model, the diffusion, so how well it's able to diffuse inside, is related to the rate constant times L squared, the constant. That's just a constant, like the length, the hopping length. And so that diffusion is related to how fast they're moving. And then that rate is related to free energy. And so free energy is just the amount of work it takes to get from the bottom of the hill to the top. Like that's how much work it takes to raise that potential energy, to get that potential energy. And so here in this equation, we can see that the rate constant is related to the free energy. And that makes sense, right? Because when we're diffusing, when the hydrogen's diffusing inside, the diffusion depends on how easily it's able to go from the left cage back to the right cage and from the right cage back to the left cage. And so if it's harder to push through, if it's harder for the hydrogen molecules to push through the water to go from one cage to the other, that hexagonal face, and if it takes more energy, then the diffusion is going to be harder. So that's why this is important, that to know the free energy. And we can actually see the effect of tunneling and like 0-point energy in these two graphs. So this was from like another research paper by the lab, and you can see tunneling in the second row of graphs. So it just it doesn't even cross the classical energy barrier, just tunnels through. So you'll see that it flattens out. So the red one is the quantum free energy profiling, and also in the 0-point energy, like you can see a gap here. So. And that's also visible in the images at the bottom. So tunneling, we can see that the molecules are more delocalized, so they're like the beads are like everywhere, so they're in the right and the left cage. And so for 0-point energy at like the higher temperatures, you can see that they're more localized, and yeah. And so my research project, I combined, I used the architecture that combined the path integral molecular dynamics and neural networks to do this, to get a full quantum description of what's going on inside the clathrate. And so the methods that I used were d-affet simulations, and so those are just regular molecular dynamics simulations, but they introduce a new set of variables that are kind of separate from the system itself, but like they help the system in that they add artificial energy to cross the energy barrier, and they obviously unbias it because then that wouldn't be real, right? And so my research project was to test 8 different occupancies, and so occupancies are just like how many molecules are in each cage initially. So we see like 2-2 and 2-3, 3-2. So those are how many are in the left cage initially, and then in the right cage initially. Those are the second digits here, and then the arrows just represent what it would be like if a molecule from the left cage moved over to the right cage. And so the materials, well, this was a purely computational project. And so like I obviously needed my computer, and I connected to supercomputer clusters because my laptop wasn't enough to run those simulations. We needed more resources and computational resources and processing power. I also had bash scripts to run the simulations. I installed VMD, which is Visual Molecular Dynamics. It's an application that allows me to see these simulations, and Python and TCL/TK scripts to analyze the simulations. And so this is like a video of simulation 2-2. So there are initially 2 hydrogen molecules in the left cage and 2 in the right. So you'll see them moving around. And so you also see the 6 beads here. So for each atom. And so you can see the diffusion as they're moving from the left to the right or the right to the left. So you can see this one just moved over. And yeah, so you also see the jiggling happening. So that's kind of cool to see as well. So over to the results and analysis. So these are kind of preliminary results. So we see so these are varying occupancies, and like the qualitative analysis is that like they shift to a more comfortable and favorable arrangement, so if there's like a less energy barrier to go to the other side, then it's like easier to go, and if it's higher, then it's like harder, and like you won't see it go that often. But these hadn't run long enough, so they take like 3 or 4 days to run. And so if you let them run for like a week or like a little longer than that, you would see more accurate results. So for example, this green one should have been symmetric. So it's going from 3-2 to 2-3, so that there shouldn't be any preference, but it's not. However, like if you look at the cyan one, you see that like the energy is higher for like the new formation, the new occupancies, which like aligns with the qualitative analysis. And so the bottom graph is the result of the labs, so like that's a little more accurate, and that's a more accurate version. And so future work would be to test a broader range of temperatures and run it for a little longer, so longer simulation time, and then extend the range of hydrogen occupancies to get a more complete picture. And I want to thank my mentor and Alan, the graduate student, and then Clover and the course assistants, and GSTEM, Catherine, and NYU. Thank you all so much.
Alright, thank you, Siri. Everyone's ready for the pop quiz on quantum physics? I'm just kidding. Any questions for Siri?
How did you decide how many occupancies to use in each cage, and how do you think changing that number would affect your data or results?
So I think like adding more occupancies would actually made it like lowered the energy barrier, I think. And And so we would see that results, we would see like based on like the heights of the peaks here, we would see that more clearly if we ran it longer. So.
All right, thank you so much.